Well, hello there, and today's video is called Mechanical Power. Mechanical power is the rate at which work is being done. So using the convention that we've come to agree on, we'll use W for the symbol for work, and the rate, we put a dot. So for mechanical power, let's use units of, well, let's see, if we have kilojoules as our unit of energy for work, and we divide it by time, rate, we'd have kilojoules per second, or kilowatts, or, let's see, what would be another English unit? We could use foot-pounds for work. Force times distance is foot-pounds divided by time, foot-pounds per second. Or we could use horsepower. I think the conversion between foot-pounds per second and horsepower is 550. So all of these are good units for mechanical power. Now when we talk about mechanical power in thermo, we're 99% of the time talking about how much work is being done by a shaft. So one place that we see a shaft is in a turbine. Now the way a turbine works is steam comes in at one end at a very high pressure and high temperature, and it goes through a series of blades working to take the energy out of the steam, extract the energy from the steam, and turn the blades kind of like a water wheel. And when that happens, connected to all those blades is a shaft. And that shaft spins. And when we have torque, that's what the blades apply, times angular speed, movement, force and distance. Think of whenever you have work, there has to be a moving part. When you take torque times angular speed, well, what you get is power. And in a lot of different classes, they use P for power. But in thermo, we use P for pressure. So we're going to use W dot for power. Now, just like in the rate of heat transfer video, which I would have wanted you to have watched before this one, the way we are going to find mechanical power for a thermodynamic device, and a turbine is a thermodynamic device, a pump is a thermodynamic device, a condenser, so turbines, pumps, and condensers, gasoline engines. The way that we will find the power in those is to apply the first law in steady state. Well, the first law in steady state is, let's see, I know the way I wrote it last time, but I am going to put all the ins on one side. So Q dot in plus W dot on plus M dot in times H in. Now remember, we're just using enthalpy. Equals, now this is the same way I did it in the last one, except I put them all on, I put all the ins as pluses, all the outs as minuses, and set it equal to 0. Now I'm going to put all the ins on the left and all the outs on the right. Q dot out, W dot by, M dot out, H out. So in the case of a turbine, is the steam doing work, or is the shaft on the shaft, or is the shaft doing work on the steam? Sometimes this is hard to remember, but I always ask the question, does the steam or fluid have more energy at the beginning or at the end? In a turbine, it has more energy at the beginning because we're taking energy out. So we are doing work by. And oftentimes with turbines, what happens is we insulate them so that there can't be any heat transfer. And it is work by, so there is no work on. And so this equation very quickly reduces to W dot by, I'm rearranging, equals M dot times H in minus H out. Now, why was I able to not call them M dot in and M dot out? Well, that's the definition of steady state. When you have steady state, whatever goes in has to come out. This is the equation for the work being done by the steam on the shaft in a turbine. And a pump would be very similar. And this is all that we do when calculating mechanical powers in thermodynamic devices. So this is a really short video.